Let's explore one of the most fundamental properties in geometry, the interior angles of a triangle. I'm drawing a triangle that's intentionally asymmetrical. This is important because we want to show that the property we're about to discover works for any triangle, regardless of its shape or size. Let's label the three vertices of our triangle as A, B, and C. Every triangle, by definition, has exactly three vertices where the sides meet. At each vertex, two sides of the triangle meet and form an interior angle. Let's highlight these three interior angles with arcs. We'll label these angles using Greek letters: alpha at vertex A, beta at vertex B, and gamma at vertex C. These symbols simply represent the measure of each angle in degrees. There's a remarkable pattern in every triangle. If you add up all three interior angles, alpha plus beta plus gamma, you always get exactly 180 degrees. This works whether your triangle is narrow, wide, tiny, or huge. But why is this always true? What's the mathematical reason behind this consistent pattern? That's the fascinating question we're going to explore. So far, we've established our triangle with vertices A, B, and C, and labeled the interior angles as alpha, beta, and gamma. Our goal is to understand the geometric principles that guarantee these three angles will always sum to exactly 180 degrees, no matter what triangle we draw. Let's explore a fascinating property of triangles. No matter what shape or size a triangle is, its interior angles always add up to 180 degrees. We're going to demonstrate this visually using a method you could try at home with a paper triangle. Let's highlight each angle of this triangle with a different color. For an equilateral triangle like this one, each angle measures 60 degrees. But remember, this proof works for any triangle, not just equilateral ones. Now imagine we're tearing off each angle from our triangle, just like you might do with a paper triangle. If we carefully remove each corner without changing the angle measure, we can rearrange them to reveal something interesting. Here's our first angle from point A, which we've torn off and placed at the bottom. Notice how we've rotated it so that one side lies flat. Now we're adding the second angle from point B, positioning it so it continues where the first angle ended. And finally, we add the third angle from point C. Look at what happens when we arrange all three angles next to each other. The three angles fit together perfectly to form a straight line. This is no coincidence. The angles create a straight angle, which is exactly 180 degrees. This visual proof shows us that the sum of interior angles in any triangle equals 180 degrees. To make this clearer, let's draw arrows showing how we moved each angle from the original triangle to form this straight line. When we talk about a straight angle being 180 degrees, we can visualize it as half of a complete rotation around a point. Let's highlight this straight angle formed by our three triangle angles. This property is universal for all triangles. Whether you have an equilateral triangle like this one, or a right triangle, or any irregular triangle, the sum of the interior angles will always be 180 degrees. You can verify this yourself by drawing any triangle, measuring each angle with a protractor, and adding them up. Let's explore why the interior angles of a triangle sum to exactly 180 degrees by using a formal geometric proof that builds on properties of parallel lines. We'll start with an arbitrary triangle. This could be any triangle, equilateral, isosceles, or scalene. The proof works for all triangles. Let's label the three vertices as A, B, and C to help us refer to specific parts of the triangle during our proof. Now we'll label the three interior angles of the triangle. The angle at vertex A will be alpha, shown in red. The angle at B will be beta, shown in green. And the angle at C will be gamma, shown in blue. These are the angles we want to prove add up to 180 degrees. The key to our proof begins by extending one side of the triangle. Let's extend side AB beyond point B. This creates a straight line through points A, B, and our new point D. Now for the crucial step, through point C, we'll construct a line parallel to our extended line ABD. This parallel line is key to our proof because it will create angles that have special relationships with our triangle's interior angles. When a transversal line crosses two parallel lines, it creates what we call corresponding angles. These corresponding angles are always equal to each other, which is a fundamental property in geometry that we'll use in our proof. Our parallel line creates new angles at point C. Let's label them as alpha prime and beta prime. Notice how I've colored them to match our original angles. This is because alpha prime corresponds to alpha and beta prime corresponds to beta due to those parallel line properties. When two parallel lines are cut by a transversal, corresponding angles are equal. Since our line through C is parallel to line ABD, we know that alpha equals alpha prime. These are corresponding angles formed by the transversal line AC cutting through our parallel lines. Using the same principle about parallel lines and corresponding angles, we can also determine that beta equals beta prime. These are corresponding angles formed by the transversal line BC cutting through our parallel lines. Now look closely at point C. The three angles, alpha prime, gamma, and beta prime, form a straight line. Since a straight angle measures exactly 180 degrees, we know that alpha prime plus gamma plus beta prime equals 180 degrees. We've already established that alpha equals alpha prime and beta equals beta prime. Therefore, we can substitute alpha for alpha prime and beta for beta prime in our equation. This gives us alpha plus gamma plus beta equals 180 degrees, which is exactly what we wanted to prove. The sum of the interior angles of our triangle equals 180 degrees. This beautiful proof works for any triangle, regardless of its shape or size. The sum of the interior angles will always be 180 degrees, which is a fundamental property in Euclidean geometry that you'll use in many other geometric proofs and calculations. Here we have triangle ABC. Notice how we've extended the line from A through C and drawn a parallel line passing through point B. This setup will help us prove why the interior angles of any triangle sum to exactly 180 degrees. Let's identify the three interior angles of our triangle. First, we have angle alpha at vertex A, shown in red. Every triangle has exactly three interior angles. Our second angle is beta at vertex B, highlighted in green. Notice how the angle is formed by the two sides that meet at point B. And finally, our third angle is gamma at vertex C, shown in blue. These three angles, alpha, beta, and gamma, are what will prove sum to exactly 180 degrees. Now, let's draw a line from A through B and extend it. This creates what's called a transversal, a line that crosses two parallel lines. In this case, it crosses our original extended line from A through C and the parallel line through B. When a transversal crosses parallel lines, it creates corresponding angles that are equal. Here on the parallel line through B, we find an angle that exactly equals alpha from our triangle. This is due to the corresponding angles theorem in geometry. Similarly, on the other side of the transversal, we find another corresponding angle that's exactly equal to gamma from our triangle. This remarkable property of parallel lines gives us the key insight for our proof. Looking at point B, we now have three angles, beta from our original triangle, and the two corresponding angles equal to alpha and gamma. These three angles together form the angles around a point on the straight line. To make this clearer, let's visualize these three angles adjacent to each other along a straight line. We can think of this as unfolding the angles at point B and arranging them in a row. Let's place angle alpha first. This is the same as the red angle from vertex A in our triangle. Next comes angle beta, our original green angle from vertex B of the triangle. Notice how it fits perfectly next to alpha. Finally, we add angle gamma, the blue angle from vertex C of our triangle. Look at how these three angles fit together perfectly. The three angles from our triangle, alpha, beta, and gamma, together form a straight angle. And as we know from geometry, a straight angle measures exactly 180 degrees. This elegant visual proof demonstrates that the interior angles of any triangle must sum to 180 degrees. We can write this mathematically as alpha plus beta plus gamma equals 180 degrees. This relationship holds true for any triangle, regardless of its size or shape, whether it's equilateral, isosceles, or scalene. It's important to note that this proof relies on Euclid's parallel postulate, one of the fundamental axioms in Euclidean geometry. The postulate states that through a point not on a given line, exactly one parallel line can be drawn to the given line. This is what allowed us to create our parallel line through point B. The sum of interior angles equaling 180 degrees is a property that helps us solve many geometric problems and serves as the foundation for more advanced concepts in mathematics. Let's explore why the sum of interior angles in a triangle always equals 180 degrees. This is a fundamental property of triangles that remains true regardless of the triangle's shape or size. We'll start with an acute triangle where all three angles are less than 90 degrees. This is the most common type of triangle you might see in your math textbooks. Let's measure these angles. The angle alpha equals 60 degrees, beta equals 50 degrees, and gamma equals 70 degrees. When we add them together, 60 plus 50 plus 70, we get exactly 180 degrees. To see if this property holds for all triangles, we'll keep track of our angles as we transform the shape. Our angle tracker on the right will help us monitor any changes. Now let's transform our acute triangle into a right triangle by moving one vertex. Watch how the angles change while their sum remains constant. As our triangle transforms, notice how alpha and gamma both change to 45 degrees, while beta increased to exactly 90 degrees, making this a right triangle. The interesting thing is that 45 plus 90 plus another 45 still equals 180 degrees. The angles changed, but their sum remains the same. Let's go further and transform our triangle once more, this time into an obtuse triangle. An obtuse triangle has one angle that's greater than 90 degrees. Watch how dramatically the angles will change while their sum remains fixed at 180 degrees. In our obtuse triangle, both alpha and beta have decreased to 30 degrees each, while gamma has increased dramatically to 120 degrees. Notice how the increase in one angle is perfectly balanced by the decrease in the others. When we add 30 plus 120, we still get exactly 180 degrees. This confirms a fundamental property in Euclidean geometry. The angles in a triangle always add up to 180 degrees, or a straight line. This property helps us solve many geometry problems when we know some angles but not others. No matter how we reshape a triangle, whether it's acute, right, or obtuse, the sum of its interior angles always equals 180 degrees. This is why if we know two angles in a triangle, we can easily find the third by subtracting their sum from 180 degrees. Let's explore how triangles behave beyond the flat world of Euclidean geometry that we're familiar with. In Euclidean geometry, the geometry of flat surfaces like paper, we know that the sum of interior angles in any triangle equals 180 degrees. This is a fundamental property we rely on in everyday mathematics. But what happens when we move beyond flat surfaces? Does this 180-degree rule still apply if our triangle exists on a curved surface? On a sphere like our Earth, triangles behave quite differently. If you draw a triangle on a globe connecting 3 points, you'll find something surprising. The sum of the interior angles is always greater than 180 degrees. The more curved the surface, the larger this sum becomes. In hyperbolic geometry, which describes negatively curved spaces like saddle shapes, the opposite occurs. Here, the sum of the interior angles in a triangle is always less than 180 degrees. The more negatively curved the surface, the smaller the angle sum becomes. This comparison reveals something profound. The 180-degree angle sum isn't a universal property of all triangles. It's actually a special property that only exists in flat Euclidean space. The curvature of the surface directly affects the angle sum of triangles drawn upon it. Let's explore how these Euclidean triangle properties apply in the real world around us. In construction, Triangles are fundamental building blocks because they're inherently rigid. Unlike rectangles, which can collapse into parallelograms, a triangle's shape is fixed once its sides are determined. This is why you see triangular trusses in bridges and buildings. They provide exceptional structural stability. In navigation, a process called triangulation uses the properties of triangles to pinpoint locations. By measuring angles from your position to two known landmarks, you can determine exactly where you are. This principle powers everything from GPS systems to how sailors have navigated for centuries. Architects incorporate triangles throughout their designs because of their strength and visual appeal. From the ancient pyramids to modern skyscrapers, triangular elements distribute weight effectively while creating striking geometric patterns. The predictable angle properties of triangles make them reliable design elements. When we understand how triangles behave in different geometries, we gain insight into the structure of our universe. For instance, astronomers use non-Euclidean geometry to map cosmic distances, since space itself can be curved by gravity. To summarize what we've learned, in Euclidean geometry, the flat geometry we use daily, triangle angle sums equal exactly 180 degrees. On spherical surfaces like a globe, these angle sums exceed 180 degrees. And in hyperbolic geometry with saddle-shaped surfaces, the angle sums are less than 180 degrees. The geometry of the space determines the properties of the triangles within it.